Hello everyone, Christopher here with McWane Science Center, and welcome back to Sci Sparks. On today's episode, a 4,000 degree clap. Don't go anywhere. Hey, let me show you something. Ready? There. That was it. You might not have caught it, but something cool just happened. Or it would be cool if it weren't so hot. Let me start over. These are two solid ball bearings made of stainless steel, and this is a regular piece of paper. Now, watch this. There. See that? That wasn't ripped or torn or punched out. It was burned. You'll have to take my word for it, but yeah, that's burnt. But here's the rub. In order to explain why this works, I first need to explain why this doesn't. So what's the difference between steel and rubber? See for yourself. While both begin with the same amount of kinetic energy, the energy of movement, once they hit the ground, all of the steel ball's energy seemed to go away. But did it? Of course not, because that would be against the law of conservation of energy. The law of conservation of energy tells us that energy can neither be created nor destroyed. In other words, energy can't be lost, but it can be transformed. Watch. The moment I release the ball, it has no kinetic energy. But it can't stay in the air. It must start moving toward the ground. And that need to move is called potential energy. As the ball falls, that potential energy is transformed into kinetic energy, and the ball speeds up until it hits the ground and squishes. But it can't stay squished. It must stretch back out, and that need to stretch to push against the ground, that too is potential energy. Rubber is elastic. It deforms, and that allows it to store its kinetic energy. Steel is inelastic. It can't deform. So all that kinetic energy has to transform into something new. In this case, thermal energy, or heat. And here's the thing. Inelastic collisions can produce enough heat to do something truly next level. Let me show you. Here I have two heavy inelastic metal balls, one covered in aluminum and one covered in rust or iron oxide. Add the heat from an inelastic collision and there! See that hole? It wasn't ripped, it wasn't torn, it was melted. Thanks to our inelastic collision, our aluminum and iron oxide broke apart, recombined, and formed new molecules, aluminum oxide and elemental iron. And the energy that released we saw in the form of light, sound, and heat. How much heat? About 4,000 degrees. So, what's the takeaway here? Should we all start cooking our food with the power of slaps? Well, in theory, you could. To cook a whole raw chicken in a single slap, it would take a slap traveling at over 3,700 miles per hour, or nearly 5 times the speed of sound. So the next time you're traveling at Mach 5, stick to a friendly wave and not a high five. Well, that's it for today's episode. If you enjoyed this episode, let us know by leaving us a like. And to catch new episodes as soon as they're released, don't forget to subscribe. Until next time, bye.